Okay, so let's see. I want to thank the organizers for inviting me today. I'm really excited to be here. A little bit nervous, but mostly excited. I switched that was not on purpose. Mainly excited, as I said. And this talk is divided in two parts. One part about reflections on AI, and the other one, how to use deep learning in self-driving cars. And my colleague, Sebastian Ramos, will go into the details of deep learning in self-driving cars in a later talk today. So, in the autonomous driving space, you often hear people say that we're using AI to solve certain problems for self-driving cars. And this confuses me sometimes, because what do they really mean when they say that? We're using AI to do this, or we're using AI to do that. I think that they usually mean we're using deep learning. And now, if you're using deep learning, for example, to detect objects in a video stream, we've been using machine learning techniques for many years to do that. So why is that not AI, and why is using deep learning AI? Or do they mean something else? I think it is confusing, and AI is used in many different ways. Some people talk about building computer brains, and others talk about detecting objects in a video stream. It's kind of a great difference, right? So therefore, I think I'm looking forward to reflecting a little bit about AI with you guys. And before doing that, I want to stress that my background is in physics, statistics, and self-driving cars, and deep learning. But I do not have an academic background or any formal education in AI. So beware, stay critic to what I say. The purpose is to softly warm up your brains for the day to come, and to get you speculating and reflecting on what AI is. And I think that is important and fun. So literally, AI means artificial intelligence. In Swedish, that is konstgjord intelligens. So we know what artificial means. So we just have to reason a little bit about the word intelligence here. One definition of it is to say the capability of achieving complex goals. I think that's quite nice, but it's also very, very wide. It includes many things. Humans are clearly intelligent. We can achieve complex goals. We do so by perceiving our environment, by learning from observations so we can adapt to changing circumstances. We can predict consequences of our actions, which allows us to plan and to reason. All of this makes us intelligent, but we can also do many other things, like create music, and the list is long. As a physicist, I like to start with something familiar, like humans, and then go to some limit. So the limit I'm going to start with is something really stupid, something, maybe stupid is not the right word, but something which is clearly not intelligent, and I hope we can all agree that rocks are not intelligent. So that will be our limit. Now, maybe some information theorist would say you can use rocks to save some memory. Patterns of rock can be used for that, or maybe even the internal structures of rock. But they cannot think, they cannot learn, they cannot do anything. The behavior of rocks is largely captured by Newtonian physics. So to make it a little bit more interesting, we can step it up to the daffodil, which is a flower. Now, do you think that flowers are intelligent? I see some shaking. I'm going to speak for the flower. The flower is able to perceive the environment so as to sense where heat is usually coming from, turning towards the sun, so as to maximize the energy it can absorb, so it can grow and reproduce. Kind of perceiving the environment to achieve a goal. Now, it's true that the daffodil cannot learn anything during its lifetime. The only way it has to evolve its behavior is through biological evolution, And yes, it's quite a severe restriction to its intelligence. The behavior is kind of captured by the photosynthesis, which shows that you need light energy to produce sugar so you can grow and so on. But I'm not a biologist either, so let's move on to a more interesting example, the rat. The rat, some think it's cute, some think it's scary, some might say it's intelligent. What do you think? Yeah, I'm gonna pretend I'm a rat, put in a maze where I've never been before, and I'm a little bit hungry. In this maze, there are three options. I can go left, I can go right, or I can go straight ahead. So I know nothing about this maze. The only thing I know is that I'm hungry, so I'm not gonna sit around. I'm gonna go somewhere. So I'm gonna go left, and after a little while, maybe there is a hot plate. I step on it and I burn my paw. So this is really not a nice place to be. Going left was a mistake. I'm gonna head back to where I came from, and then I'm gonna go right. Maybe I'm lucky to find some food here, some delicious cheese. So I can eat, I can exploit being to the right in the maze, and I can enjoy life. But maybe it gets lonely, and who knows, if I was to go straight ahead, I might find friends, or at least other rats. But that could also be a deadly trap if I go there. So now I'm stuck with this, what should I say, dilemma. I can exploit being to the right, or I can explore. Who knows what I will find? The behavior of this rat is largely captured by Neisser's perception action cycle. So the rat is using its knowledge to direct exploration, which allows it to sample the environment, which modifies its knowledge. So I know being to the left is not good, so I'm gonna go right and explore. Here I find cheese, so I'm gonna update my knowledge. And by that, I can build a mental model of this map, of this maze, which allows me to plan my life in the maze. Now, the interesting thing is that Neisser did not propose this description to explain the cognitive thinking of rats, but humans. So this concludes my little exploration into biological intelligence. And I'm going to conclude by offering this way of looking at intelligence, which you may or may not like, but I get to speak. So I was for a long time thinking about whether I should put ability or intelligence on the right axis, and maybe it doesn't really matter. You can take this and you can do whatever you want with it, maybe update it, adding more axes. Anyways, the rocks are in the origin. They are not intelligent and they cannot do many things. They cannot do anything. While the daffodil actually has some specific kind of intelligence, it's goal-oriented at least. So it has some ability, but can only do one thing, turning towards the sun. The rat, on the other hand, it's quite intelligent, and it can do quite many things. It can actually learn to play very simple games and so on. I think maybe there is no principal difference between rats and humans, but we are more able and intelligent, and we can generalize and do more things. I will come back to this when I've talked more about artificial intelligence. So back to AI. So we have this computer or this machine or this agent or whatever you want to call it, something which is at least not made of carbon. That is, it's not biological. It gets some input signals or stimuli, does something with these, and produces a response or an action or something. Now, some people working in AI think that to define what AI is, we need to look into this machine. It's all about how this machine operates, how it thinks, that matters. So Cédric Villani, which is this famous, brilliant French mathematician, he just finished a report to Macron in France, a public report, a very important report, which will probably influence the lives of many people. It's about artificial intelligence and how France and Europe can become great at AI. it's interesting to see what he defines to be AI. He says, fundamentally, AI refers to a program whose ambitious objective is to understand and reproduce human cognition. Well, this is not just detecting objects in a video stream, right? This is quite a big goal. Others think that it doesn't really matter what happens in the box. We don't have to reproduce human cognition. We just have to look at the actions of the machine. And you know the Turing Test, where you have this human who's chatting with someone. Now this someone could be a human or it could be a machine. And if the machine is able to fool the human to think that what I'm chatting with is actually a human, then it passes the Turing Test. And this is a really difficult test. I think both of these approaches are fine, and they have been big streams within the AI research in the last 50 years. But they're both human-centric. You may argue that in the space of biological intelligence, human intelligence is just a small part. And we just saw that rats have some intelligence, and maybe even the daffodil, even though I saw a lot of shaking of the heads. And also the space of biological intelligence is probably very narrow compared to the space of all possible intelligence. So why limit us to this? We can still seek inspiration from looking into animals and looking into humans. I think that's the way to go, definitely. But I stole this from Russell and Norvig, who wrote kind of the Bible in AI. And what they propose is to also think about thinking or acting rationally, instead of just thinking or acting like humans. And thinking rationally has given rise to symbolic AI and the logicist approach. And it's been really successful, and it's been dominating for many years in AI. Now, there is some restrictions into this approach because it has problems dealing with uncertainties. And uncertainties is all around if you want to act in this world. So if you want to be using machine learning or statistical Bayesian approaches, you should actually go down to this box of acting rationally, which is to say, do the right thing or act as so to achieve the best possible outcome or the best expected outcome, which is kind of coming back to where we started when we defined intelligence as the ability to achieve complex goals. Rationality also, you can look it up and you can see that it's easier to define mathematically than intelligence. And maybe it is a stricter definition as well. Oh, I should go back here. So I think all of these still are looking at building something quite grandiose, like autonomous rational agents or human brains in computers. To do that, you need to have many building blocks, like you may need computer vision or natural language processing or speech recognition, and the list can be made long. All of these things are subdomains in AI. And to solve them, you have this AI toolbox of concepts and tools and methods that you can apply. And you can take from that and build an intelligent system, an AI system. A very important tool here is machine learning, or set of tools. And within that set of tools, there is the smaller set of tools, deep learning. Now, I don't know, just because you're using either of these tools, if it makes your system intelligent. It's up to you to answer that question, I think, today. But I think in the media and in the debate, and also listening to people from various companies, some refer to AI as anything in the toolbox, or particular things from the toolbox, and some refer to these intelligent systems. And there is a difference here. The state of the art of AI and the revolution, you might say, we're in, is to a very large extent about deep learning, various approaches using deep learning. And it's been really successful within machine translation, natural language processing, speech recognition, and so on. And like computer vision, which is this whole field with its own conferences and so on and so forth. One very exciting example is AlphaGo Zero, this reinforcement learning agent which learns to play Go better than anyone else on the planet without any knowledge about the game. It just plays against a copy of itself and learns, and within a few days it masters the game of Go. It's really fascinating that it's achieving superhuman performance. So humans are able to build this architecture or program that can learn to play better than humans. But they are all very domain specific, all of these examples. So if you map it out in this space over intelligence, or this graph over intelligence, you find AI today down with a daffodil on very specific tasks. Some AI today is really competent, superhuman in its performance, and it's learning, and it's exploring, and it's exploiting, and it's doing all these things that we kind of relate to intelligence. But then there is this gray box in the upper right corner next to Alan Turing that some call artificial general intelligence. And that we can have a whole talk about that, right? But it's intelligence that is comparable to humans on all things humans can do, like driving a car, playing Go, identifying objects in video streams, and so on and so forth, processing language, understanding language. I believe it's kind of a great leap from where AI is today until we are at AGI, at Alan Turing's level. And that it will require breakthroughs in a number of different topics in the AI toolbox until we get there. But we may get there, and we may get there sooner, we may get there later. And I think it is important to take this discussion of what AI is and what we can expect AI to become and what we want it to become. And we in this room have a responsibility here to talk to others in society. And I'm pretty certain you will see more and more politicians talking about AI in media. And they will not define what they mean by this. And if we communicate that it's about building a human brain but in a computer, and we say we're using AI to solve this problem, like driving a car, what will people think? There is like this real kind of artificial intelligence here. Who controls it? So hopefully you found this exploration a bit amusing, and maybe it gave rise to some thoughts, and that was the intention. I'm pretty certain many of you disagree to some of the things I said, and it's fine, right? I expect that. I also want to say that AI today, what's happening now, is really exciting, very, very useful. It gives rise to exciting research, great business opportunities. And it's so fun to work in this space. And self-driving cars is one of the examples. And if I remember correctly, the next slide is about self-driving cars. So I'll just do a time check here. Okay. Are you awake? Good. So now I'm going to be the carpenter who only has a hammer, which is the scientist who only knows deep learning. And I want to help out building a self-driving car. So how can I help? Where can I apply deep learning, right? I'm not going to talk of any of the other very important concepts that we also use to build self-driving cars. And I come from a company called Zenuity, who's developing software for self-driving cars. It's good to know. So today you will find many companies able to demonstrate really capable self-driving cars in real traffic. It's very inspiring. The only thing that remains is to do it in a safe and robust way. Now this can be easy, or it can turn out to be very, very difficult. Well, it's not easy, but the question is, how difficult is it? To make the car safe, the perception system is really important. We have to have a 360-degree sensing system which is robust to failure cases and to various contexts in the environment. And to do that, we believe that we have to use LiDARs, which are laser scanners, cameras, radars, maybe ultrasonics, GPS sensors, communication devices, and so on and so forth. All of this makes the self-driving car a very complex system. And it is a complex system with extremely high safety requirements, which makes building a self-driving car an extremely challenging task. So how would you go about it? Well, you could feed all the sensory input into some deep neural network, which is trained to output steering requests, brake requests, and acceleration requests. And one way to train it is to just have it imitate humans. So humans are driving like expert drivers, and then the network can be trained to do what the human is doing. This idea was brought forward in the 80s. It was reworked in early 2000s and then made into fashion again by a certain company a couple of years back. And it's really amazing to see how well this car can learn to drive. However, to train it to cover all the difficult and tricky corner cases requires extreme amounts of training data. And if someone changes the traffic rules, what would you do? You have to, we have to retrain it. And that requires a lot of driving, like insanely much driving actually. And there is no understanding about why the car is behaving the way it does. So let's say you have an accident and someone is severely injured. You cannot say why this happened, you don't know how to fix it. But you have all these cars out there still driving around. I think it's not acceptable. We're not going this way. Instead, we decompose the problem into functional building blocks. So we have a sensing or perception layer, and then we have a sensor fusion layer where we combine the information from the different sensors, and then we have decision and control. It's a little bit simplified perhaps, but generally this is the case. I'm also not going to talk about mapping and localization today. Actually, there are so many things about the self-driving car I would like to talk about that I will not talk about. But Sebastian will go into more details, so you can go to his talk if you find this interesting. So, with this functional decomposition, we can start to reason about where can we apply deep learning in a good way. And I'm going to go right into the answers today, and then I'm going to provide some examples for you. I'm going to claim that for sensing, and in particular for computer vision, deep learning is needed to reach the level of performance that we want. And it's a great tool. I think deep learning also have an important role to play for sensor fusion. And I'm going to provide some examples of that, or at least one. And then for decision and control, it's a really exciting topic to use deep learning and reinforcement learning or related techniques to actually make decisions and plan the driving. But it's more of a research kind of thing, at least to the best of my knowledge. And if I have time, I will talk a little bit about deep reinforcement learning as well. I'm going to start with vision, and most of my examples come from vision. This is where we have the most people working at Zenuity. It's the lowest hanging fruit, it's very important, and deep learning is a great tool. So, computer vision. What does an image look like to a computer? Well, it's basically three matrices. You have three channels, the red channel, the green channel, and the blue channel. If you have 1 million pixels, you get 1 million numbers in each matrix here. Computer vision is all about extracting useful information from these numbers. Well, that same image looks like this to a human. It's quite interesting. I like to say that we immediately see it's a car, but then my colleagues corrected me. No. It's a lot of processing going on in the brain, right? Humans evolved, or animals evolved, over millions of years to be able to see and interpret this image. This is why it's a much harder task to train a neural network to do the same computer vision tasks as humans can do. It's much harder than training it to play Go. Go, humans have not evolved to play Go or chess or any of these games. We just came up with them for fun. But to actually sense our environment, we are great at that. Now you may argue that certain tasks within computer vision, like if you are looking at classification of images, like here, say this is a car, and you narrow it down to a number of objects and you have some training data, yes, then deep learning can today reach superhuman performance, but it's a very constructed problem. Humans are also great at detecting objects and localize them in an image like this. And we can easily segment out the borders. No effort at all. This is really hard for a computer. I'm not going to go into the details of deep neural networks since I think most of you have a good understanding of this, but basically you have this input coming in, you process it in steps, what we call layers, and if you have many layers, we call this a deep network. And typically the networks that we use have somewhere more than 10 and less than 100 layers, but there are examples where you can use 1,000 layers as well. So here is an example of how we can use deep learning. This was developed together with Autoliv, which are now called Veoneer. So we're using a deep neural network to do semantic segmentation, to detect the drivable road, and we visualize this with blue pixels. Yellow is lane markings, green and red, which is a little bit hard to see perhaps, are the edges of the road. This is very useful when building a self-driving cars. Now we can detect where we can drive. It's not just the absence of objects. Here is drivable surface, and here are the lanes. This was really difficult to do with the monocular cameras before deep learning. And you can add more classes to this as well. Here is an example with 10 classes. You can have 100 classes if you want. It's just more cumbersome to annotate the data, which is a very important aspect if you want to industrialize deep learning. We can use neural networks, deep neural networks, to detect objects. And the big upside from more traditional machine learning techniques is that they are very good at detecting objects from different angles and when they are partly obstructed from sight. And they easily scale, so we can add more and more objects like pedestrians and cyclists and sign and whatnot. This network is also able to kind of accurately estimate the distance to each object. We don't fully understand how it does that. Of course, we give it the ground truth using LiDARs or radars, but I wouldn't say magic, perhaps, but it's quite kind of amazing that it can estimate distances this good, which inspired us, and others, I should say, to try and estimate the distance to each pixel in an image. So here you see the depth map from a monocular camera. I'm not claiming that the distance estimates are as accurate as from a laser scanner, because they're not. But you see, you can easily segment out objects from this depth map. Without knowing what they are, we see here is something. So from deep learning, we are able to build a general object detector using this approach. And that is also a very, very important building block for self-driving cars. And you want to be able to detect these general objects using different sensors, because if one sensor stops to function, you have to rely on the other. Okay, now I come to an example what we can do using LiDARs. So a LiDAR, in this case, it's a Velodyne 64. It has 64 laser pointers, and it scans around like this all the time. And every time a laser beam hits something and it's reflected, it gets a measurement of the distance to this point where it was reflected. And it builds this point cloud. This is what you see here, the point cloud from a LiDAR. What you can do now is to look at this point cloud from above. And you can discretize the space into this cell, a grid world maybe, which allows you to use conventional two-dimensional convolutional neural networks, the ones kind of networks we use for computer vision. And instead of sending in red, green, and blue, you can send in various statistical measures like the average height of all the reflections in a grid cell and so on. And we did this project together with researchers at Chalmers, where we are feeding in the LiDAR top view like this into a neural network, and this is what we get out. What you see on the top here is just a reference camera. And the network does a very good job at detecting the drivable road. So now I have showed you that we can do this with vision, and we can do this with LiDAR. So now we have redundancy of detecting drivable road. My final example into sensing comes from sensor fusion. So here we are using a combination of camera and this Velodyne LiDAR to detect objects. We're using the camera to detect objects, and then we're using the LiDAR point cloud and another neural network in the point cloud to estimate 3D bounding boxes, giving us the distance, the orientation, and the size of each car here. And then the result is back projected into the image. So what you see here is just the projection of the results from the LiDAR point cloud for visualization. This example is, there is no tracking here, it's just frame by frame, the results. And this goes for all the examples I have been giving here today. So you can do a lot of post-processing of the outputs to stabilize results and improve them. But this is good. I think this is really good, and it's very, very useful for us. Okay, I still have time, that's good. This leads me into decision and control. And okay, so at Zenuity, we have a lot of competence in the area of control theory. And we have built some really cool driver assistance systems. And you can say you can start from cruise control, which is just keeping the car at a fixed speed, and then you can improve on that to build the adaptive cruise control, which can keep a fixed time gap to the car in front of you. And then you want to build increasingly complex and advanced driver assistance functions. But if you use control theory, when you start to get into intersections and roundabouts and merging of cars in lanes and so on, you will have more and more rules that you need to take into account, and it's becoming increasingly complex. So maybe learning to drive, for example, through reinforcement learning, offers an interesting alternative. Let's talk a little bit about the pros and cons of that approach. So you can use deep reinforcement learning or reinforcement learning to generate policies, basically how to act, plan, and how to act in the world. This is great for playing games, for example. Now, the problem with the reinforcement learning is that the learning is very slow when you have a big state space. So if you look at this example of Pac-Man, when you have 20 by 20 cells in this grid world, that's 400 cells in total. Now, there can be food or no food in each cell, thus giving rise to 2 to the 400 different food combinations from this simple game. It's a huge state space. And in reinforcement learning, you typically want to know how good it is to be in each state. And it's just infeasible to learn because the state space is too big. What you instead can do is to use knowledge of the game and symmetries in the game to come up with some handcrafted, representations of the state space. So instead of caring about whether there is food or no food in each cell and where the exact location of each ghost, you may instead say, what is the distance to the closest ghost, and is there food in the next cell or not, and maybe some more information. That's actually all you need. Then you can train a reinforcement learning agent to play this game better than a human. But if you ramp it up to chess or Go, those games are so complex, it's kind of impossible, or at least super hard, to handcraft good representations of state space. And this is where you can use deep learning instead. You can have a deep neural network learn a good representation of state space and learn how good it is to be in each of these states. Now, what is the main difference of games and driving a car? I would say playing games, you have a really simple and clear reward function. Either you want to maximize a score or you want to win the game. That's it. And this enables us to make very good use of reinforcement learning. But driving a car, you want to go from point A to point B in some efficient, comfortable way without violating traffic rules and without putting anyone at risk, perhaps. How do you write that down into a reward function? This is the challenge. And one way to go about it is to not try and write a reward function for all driving, but rather look at the complex scenarios that you encounter. Maybe we can use reinforcement learning just when we want to enter a complex intersection and try to build a reward function for that for intersections. I will not have time to play this example of where we simulate this, but I think the main message was to say that constructing the reward function is really tricky. And to do reinforcement learning in a safe way, guaranteeing safety, is also challenging. But it is a really cool tool, and it is useful for many things. And we are looking into this as well. So, my final slide is about artificial general intelligence and self-driving cars. So some influential people in this autonomous driving space think that we need an artificial general intelligence in order to build a self-driving car that can cope with all driving contexts. Consider, for example, this is sometimes called SAE level 5. So consider this example. You're standing behind a tram. Now the tram may be broken and may be stuck here for hours. Or it may be that the tram is just about to start again. As humans, we tend to use different cues from the environment and experiences in the past to reason about the situation and to make a good decision on how to act. It may be that the conclusion is we have to break some traffic rule to get out of the situation. In this case, we may have to reverse against one-way traffic. And you can construct numerous of these challenging scenarios where you actually have to be very intelligent in order to find the good solutions. Deep reinforcement learning and deep learning alone are not artificial general intelligence. So this means that until we get to that, we need to either constrain the operational domain of self-driving cars or offer some human assistance when needed. But still, I think with the tools we have at hand, we can come a very long way. And you may even attempt to put self-driving cars on the road quite soon that want to cope with all driving contexts, but then you need to provide some manual assistance in some way when needed. And it's very exciting to be part of this journey, and I'm really curious to see what kind of self-driving cars we will see out there and when they will come. That was the final slide of my presentation. Hopefully we have a few minutes or time for a few questions. Thank you.